All right, people, we have our first installment here in our next unit, which is thermochemistry, okay? And thermochemistry meaning thermo, meaning heat, and chemistry, of course, is what we've been studying all year. So we're going to dive into this idea how heat or energy plays a role in our chemistry. To do that, we need to talk about what is energy, all right? And energy is not as concrete as mass is, or volume is, or time, or even temperature is, because energy isn't something you can put your hand on and carry around in a basket. The way that I like to think about energy is going back to almost our physics definition of that, which is the ability to do work or cause a change. So anytime we have either a chemical or a physical change in our universe, there is a transfer or a shift of energy of somehow. So you can't create a change without some sort of energy being inputted or taken out or affected there, okay? And we can track that amount of energy that we need either through physics problems or through a chemistry problem scenario, okay? So we can actually track these changes of work in joules to make energy happen, right? The unit for that is the joule. Now, a joule is a really small amount of energy, so a lot of times we actually talk about those in kilojoules. To give you some other comparisons, a joule is the energy required for a 1 watt per second. Okay, so if you're running a 1 watt light bulb and you only had it on for 1 second, that'd be a joule of energy that you just used. Another way of looking at it, if you ate a green pea, that's about 1,000 joules of energy. Okay, so kind of give you an idea of how small that really is. You may have heard of calories before. So calories, 1 calorie is 4.18 joules. Now be careful because the calories that they list on food labels are actually used with a capital C, which is a food calorie. And what they've done is they've actually multiplied them, okay? So for every food calorie that you see on a label, so let's say you have a bag of popcorn that's a 100-calorie bag of popcorn, that's actually 1,000 calories times 100, okay? So it's actually 100,000 calories that you would use in a scientific setting. But in the food setting, they divide it by 1,000 to get a food calorie, and then that's what they list it at. So they say it's 100 calories, okay? Just kind of be aware of that. Knowing that, that means that to get 1 food calorie, that would mean we'd have 4,180 joules. So it kind of gives you a good idea how small a single joule really is. And because of that, we often work in kilojoules, okay? Okay, that brings us to how energy and chemistry kind of link back to each other. And first thing we want to do is talk about the 2 main forms of energy as we go through this unit. The first is going to be kinetic energy. And kinetic energy is any time that we have moving energy, okay? Now, our focus in chemistry is often on temperature because it's our way to measure the average kinetic energy of a system, okay? So if things warm up or there's higher temperature, we know there's more kinetic energy there. If things cool down, we know that it's colder temperature and there's less kinetic energy on average in that system, okay? The other one is potential energy, which is known as the stored energy, right? Kind of like if someone says, you have lots of potential, but then you know it's followed with a but because you're not using that potential, right? So that's what potential energy is. It's energy that is being stored or not currently in use, okay? So our focus in chemistry is the fact that chemical bonds can actually store energy for us, okay? So it's kind of nice because the actual bonding of things and how much energy is stored there in comparison to other things that store energy in bonds, we can manipulate that, all right? So one of the cool things that chemists get to do is we manipulate this relationship between how much energy is stored and how much is being used, and as a result, we can get energy to do work for us, or we can purposefully store it for later use, okay? Next thing we want to talk about is a review of temperature and how that compares to heat, okay? So temperature, we already know, we've talked a lot about it. It's the average amount of kinetic energy in a system. We know that within that system, particles are moving different speeds. They have different energies, but if you average them out, that's the temperature. Heat is not worried about whether it's hot or cold, okay? Very quickly in this unit, you have to detach yourself from the idea that heat means hot and no heat means cold, okay? It's going to get you into trouble. You also need to detach your physical presence to these scenarios. And one more thing, you can't think of everything as being water, okay? These are the things that get students into trouble in this unit because we think of like freezing always being cold or boiling always feeling hot to us because it's actually a comparison of our body temperature to water's freezing points and boiling points, which is just 2 things in our universe, okay? If you can detach yourself from it and look at it more as a spectator from the outside, it'll be better for you, okay? Keeping that in mind, heat is actually a measure of the total energy in a system. So we're going to add up all the energies of all the particles present in whatever system we're studying. That's our heat, or it's our energy content. Okay, so when I say what's the heat of this, I'm not saying is it hot or cold. I'm asking you how many joules are there. I'm asking you what's the energy content inside this substance or this system that we're working with. To give you another idea about this, which of these two is hotter? Okay, we have the Atlantic Ocean, that's a whale's fin, by the way, and we have a hot tub. Most students would say the hot tub is hotter, Mr. Dirksen. It's 102 degrees Fahrenheit versus 50 degrees Fahrenheit. And I'd be like, yes, you're absolutely right. It is hotter. It has higher temperature, higher average kinetic energy for that system. But if I ask you which one has more enthalpy, that's our fancy word for heat, your answer correctly would be the Atlantic Ocean. Yes, it is colder. Yes, if we touch it, it feels cool to the touch to us, where a hot tub feels warm to the touch to us. But again, we have to remove our own senses from this scenario. And if you think about it, what is the energy content of the entire Atlantic Ocean? If you added up all the energy possible in those oceans, it's way more than the hottest hot tub is going to be. Okay, it's colder by temperature, but the actual heat content available, or the energy available to be used there, is way higher. Okay, and that's actually a good thing because our oceans help regulate overall temperatures in our environment because of that. Now, one other term that we got to review here as we begin our next unit is the idea of being endothermic or exothermic. So are you releasing heat energy or are you absorbing it? And we're going to start with endothermic, okay? Endothermic, again, the endo means in, okay? Think of like endocrine systems in biology, or endoskeleton versus an exoskeleton, okay, in biology. So if you are an endothermic reaction, you're bringing energy in. The way we symbolize that mathematically, we say that the change, our delta here, in energy is a positive value. Okay? When we talk about energy, we're going to use it the same way we do money. So anytime we gain energy, we're going to call that positive. Anytime something loses energy, we're going to call that negative. Just like if you work a job and you get your paycheck, that's positive money for you. If you spend that money, that's negative money for you. Same idea. It's also important as we look at these terms of endothermic and exothermic is to define the system in comparison to the surroundings. Okay, we always want to be focusing on the system and what's happening to the system, not the surroundings, which is tough sometimes because sometimes all we know about is the surroundings and we have to infer what's going on in the system because of what we know is happening in the surroundings. And I'll get some examples for you as we go through this unit. Okay, so let's go through a couple questions. Does it mean that endothermic things feel cold to the touch? Hopefully that threw up a red flag right away because all of a sudden I'm asking you how do things feel to the touch. And I've just told you several times that we have to like extract ourselves from the scenario. So the answer here is no. Okay, feeling cold or feeling hot to us has no bearing on if it's endothermic or exothermic. Okay, it is possible that it is, but it could be the other way around. In fact, as soon as we touch it, because we're not neutral, we actually have heat of our own. We're actually changing the energy system by touching it. So that's not something we would do in the first place. The second thing we want to look at is what about this idea of phase changes and reactions, that kind of stuff? What is considered endothermic? What's considered exothermic? So let's go through the process of phase change first. Freezing, melting, boiling, condensing. Okay? So in terms of different directions up and down the heating curve, all right? If we are freezing or melting, one of these two things is endothermic, one is exothermic, okay? One of them absorbs heat energy and one of them releases heat energy. Again, before you answer this, you need to detach yourself from your impression of freezing and boiling with water because not everything freezes below or at 0 degrees Celsius and not everything boils at 100 degrees Celsius. So it can't be a comparison of your experience with water to answer this question. Instead, ask yourself something very simple. When you freeze, does the water or the chemical or the iron or the ethanol or whatever is freezing, does it absorb energy to freeze or does it have to release energy to freeze? Okay? And you know this because you've studied IMF and how that works. Same thing for melting. Okay, so get an answer in your head. Which of these two is endothermic? Freezing or melting? Pick one now. Okay, here we go. So when you freeze, you are going from liquid phase, higher energy, to solid phase, lower energy. So the only way you can transfer from high energy to low energy is to release energy. So when you freeze, you're exothermic, which means when you melt, that's our right answer here. Melting is actually endothermic, which you might think, whoa, how is that possible? I'm melting. That kind of gives me this impression of releasing energy, but it's not, because you're still attaching yourself to water. When you melt, you go from a solid, low energy, to a liquid, higher energy. Well, how do you get to higher energy? You have to absorb some energy. So because the melting process requires energy absorption, it's endothermic, okay? Also remember, when you freeze and melt, there is no temperature change. So we're not talking about warming things up or cooling things down. We're talking about a change of state here, okay? When you freeze or melt, the temperature stays the same at 0 degrees Celsius for water. Stays the same at 5.5 degrees Celsius for benzene, okay? For those. Second one here. What about reactions that warm up or cools down? Okay, you're running a chemical reaction. You're not putting a hot plate on it. You're not using boiling water. You're not doing anything to it physically to warm it up. It's not like you're cooking something, okay? You just pour two things together, it reacts, okay? If that reaction warms up or cools down, which one is endothermic? Again, let's ask ourselves the question, where's energy, what's going on with the energy? Is energy being pouring in or is energy coming out, okay? So if a reaction is warming up, okay, that means the chemistry or those bonds inside of there actually have to be releasing heat energy, okay? And the only place they can release the heat energy is into anything that's in the surroundings around it, which would be our thermometer or our tool that would be measuring that reaction. In fact, it releases heat energy to the actual solution in which it does the reaction into very often, okay? So the surroundings will warm up, the thermometer will warm up, the water that the chemistry is being done in warms up because the reaction itself is releasing the energy. So because the reaction is releasing the energy, it is exothermic. If the reaction cools down, that means it has to pull energy in from its surroundings. So it's pulling energy from the thermometer. It's pulling energy from the water that's in the solution or from the air that's around it. And as it pulls that energy in, okay, it cools down those surroundings. So it cools down the thermometer, it cools down the water, it cools down the air. So because it's cooling down those surroundings, okay, that reaction then would be endothermic, all right? So reactions that cause a warm-up are exothermic. Reactions that cause a cool-down are endothermic. Now, we talked a lot about this already, but let's just kind of reiterate with the exothermic stuff. So with exothermic, again, energy is being pushed out. So in this case, it's kind of like spending your money, so you go negative. Okay, so if the system is losing energy, again, we focus on the system is losing energy, it's a negative thing for the system, okay? Which then, of course, would mean that, again, we don't want to deal with our own touching. So no, exothermic things does not mean hot for us, okay? It could be cold, it could be hot, we don't care, we're not going to touch it anyway, okay? And then take a look at this idea of boiling versus condensing. Running the same thought process, when you boil, you're going from a liquid to a gas. The only way you can go from a liquid to a gas is to give it more energy. So energy has to be going in. So boiling would be endothermic, which is something we've already learned, okay? We talked about how boiling or evaporation or sweating are all endothermic processes because they are absorbing energy to become a gas, which means condensation is actually an exothermic process because when you go from a gas back to a liquid, you actually are releasing heat energy, okay? And those kind of things. Which then brings us down to our reactions. So reactions that warm up, that means that they are expelling energy to the surroundings and warming up those surroundings, the water, the thermometer, the air, whatever it happens to be. So reactions that warm up on their own are exothermic. Reactions that cool down on their own are endothermic. Now remember, I say on their own, because if we use a hot plate, or if we use an oven, or if we use ice, or we use something to externally change it, that's a different ballgame, okay? All right. We're going to end here, and then we will start next time with enthalpy in more detail. Thank you.